Welcome to this lecture on second-order differential equations with variable coefficients. Today, we'll explore techniques for solving linear second-order ODEs where the coefficients are functions of the independent variable rather than constants. We'll cover three major techniques for solving these types of equations. First, the Cauchy-Euler or equidimensional equations. Second, the reduction of order method when we already know one solution. And third, the power series method for analytic coefficients. Let's begin with Cauchy-Euler equations. An Euler equation has the form x squared y double prime plus a times x times y prime plus b times y equals 0, where x is greater than 0 and a and b are constants. This type of equation is special because the powers of x in each term decrease by exactly 1 as we take derivatives. To solve an Euler equation, we make a clever assumption or ansatz. We try a solution of the form y equals x to the power of r, where r is a constant we need to determine. Taking the derivatives, we get y prime equals r times x to the power of r minus 1, and y double prime equals r times r minus 1 times x to the power of r minus 2. Now, we substitute these expressions into our original differential equation. After substitution and simplification, we get r times r minus 1 plus a times r plus b equals 0. Rearranging, we get the characteristic equation. R squared plus a minus 1 times r plus b equals 0. The nature of the solutions depends on the roots of this characteristic equation. We have three cases to consider. First, if we have two distinct real roots, r1 and r2, then the general solution is y equals c1 times x to the power of r1 plus c2 times x to the power of r2. Second, if we have a double root, r, then the general solution is y equals c1 times x to the power of r plus c2 times x to the power of r times natural log of x. Third, if we have complex conjugate roots, alpha plus or minus I beta, then the general solution is y equals x to the power of alpha times the quantity c1 times cosine of beta times natural log of x plus c2 times sine of beta times natural log of x. Let's work through an example. Consider the differential equation x squared y double prime minus 3x y prime plus 4 y equals 0. This is indeed a Cauchy-Euler equation, since the powers of x match the pattern we discussed. The characteristic equation is r times r minus 1 minus 3 r plus 4 equals 0, which simplifies to r squared minus 4 r plus 4 equals 0, or r minus 2 squared equals 0. We have a double root, r equals 2, so the general solution is y equals c 1 times x squared plus c2 times x squared times natural log of x. Now, let's move on to our second method, reduction of order. This method is useful when we already know one solution to the differential equation. Consider a second-order linear differential equation in standard form. Y double prime plus p of x times y prime plus q of x times y equals 0, where p and q are functions of x. If we know one solution, y1 of x, we can find a second, linearly independent solution using the reduction of order formula. The formula for the second solution is y2 of x equals y1 of x times the integral of e to the negative integral of p of x dx divided by y1 squared dx. Let's break down the steps. First, write the ODE in standard form to identify p of x. Second, compute the integrating factor mu of x equals e to the negative integral of p of x dx. Third, use the formula to find y2. And finally, the general solution is y equals c1 times y1 plus c2 times y2. Let's see this method in action with an example. Consider the differential equation x squared y double prime minus x y prime plus y equals 0 for x greater than 0. We're given that y1 equals x is one solution. First, we rewrite the equation in standard form. Y double prime minus 1 over x times y prime plus 1 over x squared times y equals 0. So p of x equals negative 1 over x. Next, we compute the integrating factor. Mu of x equals e to the negative integral of negative 1 over x dx, which equals e to the natural log of x, which simplifies to x. Now we compute y2 using our formula. y2 equals x times the integral of x divided by x squared dx, which equals x times the integral of 1 over x dx, which equals x times natural log of x. Therefore, The general solution is y equals c 1 times x plus c2 times x times natural log of x. Our third method is the power series method. This approach is useful when the coefficient functions p of x and q of x are analytic at a point x0. The idea is to look for a solution in the form of a power series. Y of x equals the sum from n equals 0 to infinity of a sub n times x minus x0 to the power of n plus r, where is determined by the indicial equation. The process involves substituting the power series into the differential equation, collecting terms with the same power of x minus x0, and setting the coefficient of each power to 0. This gives us a recurrence relation for the coefficients a sub n and determines the parameter r. The power series method is particularly useful for equations with regular singular points, where the power series solutions might involve logarithmic terms. To conclude, let's discuss how to choose between these methods. Use the Cauchy-Euler method when the coefficients match the x squared, x, and constant pattern. Use reduction of order when one solution is already known. And use the power series method near ordinary or regular singular points, especially when other methods don't apply. Each technique handles a different class of variable coefficient ODEs, so having all three in your toolbox is essential for solving a wide range of differential equations. Thank you for watching this lecture on variable coefficient differential equations. With these three methods, Cauchy-Euler, reduction of order, and power series, you're now equipped to tackle a wide variety of second-order linear differential equations with variable coefficients.